Hi, the lecture today is about the derivative as a function. So let's get started on that. The derivative as a function. This is going to be more of the same, similar to the last two lectures we have seen. Essentially, we go ahead and define the derivative of f at the point x to be f prime of x equals to limit of f of x plus h minus f of x over h as h goes to 0. What's the difference between this and what we just saw in the previous lecture? In the previous lecture we had a written in this place, indicating that we were just paying attention at one single point, like we were writing f prime of a is equal to limit of f of a plus h minus f of a over h as h goes to 0. Now it's only a point of emphasis that we are saying, well, once you calculate the derivative at the point a, you can take that point to be anywhere you wish. So let's start thinking about the derivative itself as a function, meaning the input of it can be changed from a place to place, and the output, which is the derivative, also going to be different. So it's just a point of view rather than anything new as far as the definition or the operation itself is concerned. So let's go ahead and explain this thing one more time on a picture. So you have a x and y here. Suppose you have a function y is equal to f of x. We have practiced a lot on the issue of finding the slope of the tangent line at some location. If I had this particular location, and I would go ahead and look at the tangent at that point, and I will have my derivative. Now we start to think, what if I let this point move somewhere else? So if I'm here, I'll have another tangent line in a different slope. If I come here, I have another tangent line and another slope, and so on. So slope on a curve typically changes from a point to a point, and this definition that we are writing here emphasizes that the derivative itself is a function of x. Let's go ahead and practice what we just wrote. Suppose I have a function f of x. Let's take a very simple one so we don't spend time on the algebra. Say x squared. Calculate f prime of x. Well, what's f prime of x? It's supposed to be limit of f of x plus h minus f of x over h as h goes to 0. Well, that's going to be limit of f of x plus h. Here I have to write x plus h squared, and this is just a copy of f of x is x squared over h as h goes to 0, and that is limit of numerator. You expand it and open it up, you get x squared plus 2xh plus h squared minus x squared over h as h goes to 0. I can go ahead and cancel these x squares. From the remaining, I can factor an h. I'll be left with 2x plus h divided by h as h goes to 0. H is cancelled, and you get limit of 2x plus h as h goes to 0, which is just 2x. Let's go ahead and digest what happened. We started with a function x squared. We went through this process to get its derivative. We are going to write the result in one of two ways. One of them is to write like this: if you have x squared is your function and you differentiate it, you are going to get 2x. So we have the derivative or the slope at all the points, and then we can put this to any use we want. Now let's make sure we don't make a certain common mistake. Suppose I ask you find equation of tangent line to y equal to x squared at x equal to, say, 3. Well, I say when x is equal to 3, obviously from here, if x is equal to 3, we conclude that y is equal to 9. Question is, well, what's the equation of the line? The equation of the tangent line, you're used to writing it like this: y minus y of a given point, which is 9, is equal to, now here I have to write the slope, times x minus the x of a given point, which is 3. Now what should I write here? What is the slope? Common mistake is to say the slope is 2x. I'll encourage you to sit down and think about where is the origin of that mistake. Slope is the value of this function at that point. That is, you have to take x equal to 3, put it here, and get the slope to be 6, and put that one here. So it would be a mistake to write y minus 9 is equal to 2x times x minus 3. This is not applicable here. First of all, this x is the x from a line. That's the x for a point on the parabola, on x squared. These have nothing to do with each other, and this is the slope that has to be calculated at the point that you want to find the equation of the tangent line. So make sure you don't make a mistake like that. It's almost always the case that you have to figure out the slope from your formula by plugging your x in it. So you just take this x, plug here, and then you get your slope. This is the slope of tangent line. And then you use that here. And then you go ahead and simplify. So I hope you don't make this mistake. In the previous lecture, we said how to write the equation of tangent line in general. If you want to write in general, you have to write y minus the y of the point. Y of the point perhaps is f of a is equal to slope. Slope will be f prime of a times x minus a. So what does that mean in this case? Suppose you want to write the equation of tangent line at the general point. Well, if x is a, then y is going to be a squared, and m, what is m? Slope of the tangent line is going to be 2a. In that case, you are going to write y minus the y of a given point is equal to the slope times x minus the x of the given point. So if for some reason you wanted to find the equation of a tangent line at the general point, in that case you use a letter other than x and y to indicate your general point. You calculate all the required quantities in terms of that letter, and then you use it in the equation of the line. So this one becomes equation of general tangent line to y equal to, say, x squared. It will be rare in this course that you'll need that. For some of the challenging problems maybe, but that's going to be quite rare. 99% of the time this is what you're going to be dealing with, and that's what you should concentrate on. Okay, in the previous lecture we talked about notation. We said we have Newton's notation for derivative. That notation was, well, find out name of your function, whatever that name is. So if the name of the function is f, use that same name. You put a simple prime notation on it. You follow it by value of the input. Perhaps in general it's x, or maybe a certain number or some other quantity. Well, there is a whole list of different notations for this topic. This is probably one of the most important topics in calculus. So different scientists work on it, and everybody had a different notation, and at least 2 or 3 of them survived through centuries, and we need to know about it. And there is another notation which is due to Leibniz, and we want to be familiar with that too. We are going to need it. So here's Leibniz notation. For the time being, we are going to write it as df dx. So that's how it's going to be read. df over dx. Sometimes is written as d dx of f. So here's the name of the function, here's the name of the independent variable of it. This d is standard, regardless of what other letters you use here. This is just the letter d. It's better not to use d in this context, because this is going to be awful to write and read. So keep the letter d out of the notation you use here. Well, this is not the end of it. If your function was y equal to f of x, Newton's notation could have been written as f prime, or could be written as y prime. In the same style here, this could have been written dy dx. So that's another way of writing this. There are still other notations sometimes people use. We are going to reserve some of these notation for other uses in the semester, but you might as well see one. Sometimes they use a capital D, so they write df. Sometimes they might put a letter underneath D to indicate what is the variable of differentiation, and so on. So essentially, any letter D in any language gets to be used to indicate some sort of differentiation, and we are better off if you get used to the notation that you see here. Right now, again, I emphasize that the kind of notation you see very often is that a function formula might be written, then we wrap it in a parentheses, put a prime over that, and on the other side we write what the derivative turns out to be. That is a process of calculating the limit of difference quotient is finalized, and the final answer gets to be written here. So our current notation for a month or so will be this. Later on, we are going to make tables of various functions and their derivatives. So we are going to have another kind of table notation for ourselves. We are going to have a list of functions and a list of their derivatives. An example would be like a function x squared is going to show up in this column, and its derivative is going to show up in this column. Let's understand again what is the concept that is being emphasized here. One way to understand the concept is to graph both of these functions simultaneously. I'm going to include some links to some nice websites that investigate the picture of a function and its derivative at the same time. You can go to those websites and play with some of the inputs, but right now let's just go ahead. X squared is a parabola, of course. So we could just go ahead and draw some parabola. If I can draw it nicely. Okay. Became a bit crooked here. Okay, this is x squared. In the graph of 2x, this is 2x. Okay, what this means is that if I pick any point, for example here, if I pick 1, the value of the function comes from x squared, so height is also 1. The value of the slope comes from this. If you take 1 and plug it in 2x, excuse me, you get 2. So function is 1, derivative is 2. If I had taken x to be 2, the function will be 4, because 2 squared is 4. Slope will also be 4, because 2 times 2 is 4. If I take 3 as my input, the function will be 9, but slope is going to be 6, and so on. So we have simultaneous access to what the function is and what its derivative is. That's going to be the first half of the course in calculus. Given a function here, how do you find the derivative of it and all the properties of that? The second half of the course will be to travel backward. If that is given to you, how do you figure out the first one? Now let's go ahead and do more practice on the first half. More on the concept and notation here. We are emphasizing these items here quite a bit, because it's very important to understand what's going on, and then to use it properly and write it properly and talk about it in a proper way. We are going to talk about operators. Okay, operators aren't just the ones who answer the phone for you. Operators in mathematics are the items, things that act on functions. Let me write it. Acts on functions. For example, if you have a function like 2x, another function that is like x cubed, you can add those two functions. There are certain operations you already know. There's operation of addition, subtraction, multiplication, division, exponentiation. These are all the things you know from algebra. Now in calculus, there are some new things you can do to functions. What are the new things? There is just the act of differentiation. So differentiation is a new operation. So you're getting an expanded view about what are the operations other than the basic operations you learned in elementary school and high school. Now we have a new operation, which is differentiation. So that's the activity we are going through here. We are operating on x squared, and our operation is to take its derivative. Here is the result of the operation. Okay, so operators are things that act on functions, and differentiation is one major new operation you see in calculus. The other one is going to be called integration, and that's going to be at the end of the semester. Okay, this particular operation we are talking about sometimes is referred to as a differential operator. For example, when you have this function x squared, you want to put a prime on top of it. That is it. That prime itself is a differential operator. The new Leibniz notation. So here's my differential operator. Here it is. Let me write it in blue color. This blue color is my differential operator. Here's another way of writing it. d dx, that's a differential operator. It tells you what is it that you want to do. You want to differentiate. What is it that you want to differentiate? You want to differentiate x squared. So d dx is a differential operator, so same as this prime. That's another way of writing differential operator, and here's the answer. So differential operator is the name of this operation that you are carrying through here. Okay, we talked about this contribution from Newton. This contribution, this notation is from Leibniz. We just keep that in view. Now, more definitions and more terminology and grammar and so on. We have this adjective in this section. The adjective for a function that has a derivative is differentiable. So what is differentiable? So here is the word differentiable. Means it can be differentiated. Means you can go through that limit process, and at the end you're going to get you got something legitimately. So it means can be differentiated. So sometimes you say, here let's use that in a sentence to see how it goes. We say f of x is equal to x squared is differentiable at x equals to 3. What does that mean? It means I can go ahead and calculate the limit of this process, limit of f of 3 plus h minus f of 3 over h as h goes towards 0 exists. So to say f of x equal to x squared is differentiable at x equal to 3 means that if you go to the trouble of finding this, there is an answer. There is a real number answer. Okay, for this to make sense, we have to talk about things that are not differentiable. That is going to make it clear. But before we go there, let me just explain one more item. F of x can be differentiated at 3, means this exists. Also can be differentiated at 3.1, 3.5, 4, any of those numbers. So we can say f of x equals to x squared is differentiable on. Now I can make a list of all the points on which it is differentiable. This one happens not to give any headache at any place. So if you want to specify that a function is differentiable on a whole set of points, that is an interval of points, you just specify your interval and you use this adjective differentiable and then say on that particular interval. So this function is differentiable everywhere. Okay, now we are going to go ahead and do what we promised. What if a function fails to be differentiable? So let's pick some examples of that. Examples of situations where f is not differentiable at a point. First, on a graph, it's going to be easier to see what might go wrong, and then we go ahead and look at some formulas as well. So here, let me draw some pictures of functions that fail to be differentiable at a given point. Among the simple functions, you know, the one that comes to mind that's not differentiable is just the absolute value function. Here, let me draw the graph of y is equal to absolute value of x. So absolute value of x, if x was negative, like -2, absolute value of it is 2. And absolute value of 2 is also 2. So that is, if you take this line and fold it at the origin and bring this to the positive section, you're going to get the graph of absolute value of x. Okay, now remember what the derivative is. It's the slope of the tangent line. So if I take a point here and consider the slope, well, slope is 1. Tangent line is just the line itself. This is true all the way here. If I take a point here and try to figure out the slope, slope turns out to be -1. The question is, what happens in between? At this point, should I go with that slope or should I go with this slope? Should it be -1 or 1? Probably a good engineer goes and takes an average, but that is a little bit not professional here. At this point, we are going to say the function is not differentiable. And we say is not differentiable at x equal to 0. So the way to understand it is that you come a tad bit to the right, you have one answer, it's +1. You go a tad bit to the left, you have a different answer, it's -1. So at this point, we don't have derivative. So we say it is not differentiable. This is an example of a sharp corner. Any function whose picture has a sharp corner at the location is not going to be differentiable at that location. So a sharp corner is indication that the function is not differentiable. It doesn't have to be such a simple function. I could have some curve that comes here and all of a sudden it just goes in a different direction. And it's obvious that the slope on the left and slope on the right are two different slopes. That prompts the notion of one-sided derivative. That is, on the left you have one derivative, on the right you have a different derivative. So here another thing that comes up, one-sided derivative. So for example, one-sided derivative here, on the left side it's going to be -1, on the right side it's going to be +1. I'm not going to say much more about that. You might see it in some exercises. I just wanted to mention. So that was one way for a function to fail to have a derivative, because the left and right are acting different. Here's another example. Which is totally different than that one. A function could behave like this. On the first look on this function, there isn't any problem with it. You can go ahead and draw the tangent line any place on it you want. There is no competition as to what the tangent line is supposed to be, as opposed to here. Here you had the one tangent line on the left, another tangent line on the right. Here you always have this one tangent line at any location you want to. But remember, derivative isn't tangent line, it's a number, and that number has to be calculated. Now suppose I try to figure out the tangent line right here, or what would the tangent line be? The way I've drawn this graph, it's kind of clear. The tangent line is just this vertical line. there's no problem with the tangent line. But what's the slope of it? Well, you know that the slope of a vertical line is not defined. Slope is infinity, in other words. So at this point, so I say if tangent line is vertical, then derivative does not exist, it does not exist as a real number as a symbol. You can say it is perhaps plus infinity or minus infinity, or depending on how you interpret it, might be both. So at this point we have a very well-defined tangent line, just a vertical line. It so happens that slope doesn't exist. What type of function would behave like this? An example of this type of a function would be, say, y is equal to cube root of x. Take a derivative of it at the origin. You'll see that slope becomes infinite. Right now it might be a bit hard for you to find the derivative of this thing, but we will come back to that later on. A somewhat similar situation happens if you have a picture like this. So again, tangent line is very well defined at every point. There's no problem with figuring out the tangent line. Here's a tangent line I can draw. If I could draw it well, here's a tangent line. Here's another tangent line I can draw. No problem drawing tangent line here. The only point that catches our eye is just right here. Even at that point, tangent line is well defined. Let me draw it in red. That's the tangent line. Again, the slope of the tangent line there is plus or minus infinity, and that is what creates a problem for us. An example of a function that exhibits a behavior like this is cube root of x squared. This type of a point where function behaves like this are referred to as a cusp. So kind of like a double pine needle. At that corner they form a cusp. So cusp situation prevent the derivative from existing, and also vertical tangent line creates the same problem. This vertical tangent line is actually quite common, and you have to be able to handle situations like this. Here's a very common situation. You might have a circle. A circle gives you that kind of a picture. If you have a circle at this endpoint, it's going to have a vertical tangent line, and so it is something to keep in mind, to know that it does happen. Okay, now I left one item for the last, which is a theorem. Theorem says if f is differentiable at a point, let's call it at A, then f is continuous at that same point. This is just practicing our notion and our language. Remember, differentiability, we are saying a function is smooth and has a tangent line, and the tangent line has a well-defined slope. Continuity was something totally different. So make sure that continuity simply meant that you can draw the function without taking your hand off the page. That was a simple intuitive version of continuity. You can draw it while you're holding hand on your page. That does not imply differentiability. Here's a very good example of it we just saw a moment ago. This function, absolute value function, is continuous. I just drew it without taking my hand off the page, but it is not differentiable, because at this point the left and right derivative are different. So remember, we are saying if something is differentiable, then it is surely continuous. We are not saying the opposite statement. We are not saying that if it is continuous, then it is differentiable. So this is a theorem. I'll let you read in the text and spend some time on it. You have to read all the statements very carefully to understand the proof itself. It's a very simple proof. Those of you who are interested in pursuing mathematics, let me know, and then we'll go over the proof together. I'll go ahead and perhaps do one example here of a function and its derivative. Here is a question. Find the derivative of f of x, say equal to 1 over x squared. I emphasize that at this point in the course, the idea is to find the derivative by the limit process. So find the derivative by using definition. That means using the limit process. So those of you who have taken calculus in high school, you still have to be patient until next chapter, where we'll change gear and go into a formula mode. Right now we have to figure out this limit of f of x plus h minus f of x over h as h goes to 0. You have to show me your prowess in using formulas going through this approach, and not to take a shortcut yet. So x plus h, we just have to put x plus h instead of x. F of x, just copy of what we had, divided by h as h goes to 0. Now I have to go ahead and patiently take a common denominator. This is x plus h squared times x squared. Here I'll have x squared minus x plus h squared, and the whole thing divided by h. I forgot my own advice. Limit of h going to 0. Now I go ahead and open the top numerator and also multiply these items. X squared, the second item I still have to keep the parentheses. Denominator, I just list them all together. H times x plus h squared times x squared. Again, I forgot. Limit of h going to 0. That indicates that it would have been better to write to do all the algebra and do the limit all the way at the very end. Okay, now we have limit of numerator. I have cancellation. I have to watch out for this subtraction. I go ahead and write, I might as well factor h. I have h times x plus h squared times x squared. Notice that it is quite rare that we need to open up the denominator to do anything, so we just don't do that. These h's cancel. I still take the limit as h going toward 0. So as h goes to 0 in the numerator, I'm left with minus 2x. Denominator, this is x squared, another x squared makes x to the power of 4. The net is minus 2 over x cubed. This whole thing would make sense so long as x is different from 0. Notice that any of these calculations that we do adds one more item to our table. So what we have learned so far is that we learned that here is how we summarize the whole activity. 1 over x, we differentiated it, and the answer came out to be minus 2 over x cubed. These are things better memorized because we are going to come across them quite often. What was another example we saw today? It was x squared. We differentiated it and came out to be 2x. So our job in the next chapter would be to make a long listing of such formulas. Some basic functions on this side, their derivatives are taken, and we record what their derivatives are. And then later on we go ahead and find the ways of making this process quick so that we don't have to do all this limit process anymore. Okay, I guess I go ahead and stop here and ask you to do the exercises of this section. Good luck and God bless.